Really glad to see you all here. I've been looking forward to this webinar this afternoon. And the process of going through the webinar and putting everything together made me realize that one, it's inaccurate for us to talk about nitrogen, and two, or nitrogen as this thing, because in fact, all these different forms of nitrogen behave so differently that we should really be talking about nitrate versus ammonium and versus amino acids, etc. But it also made me realize that if we really want to get into how nitrogen creates yield drag and all of the interesting effects and side effects that it has on plants that we often don't consider, that could be a 10 1 hour long webinars rather than just one. So there's a lot that didn't get included today, but we got plenty here. Phil, I got a message from a Don McClure that he can't hear me at all. Can you just verify that you can hear me? We did a check earlier. I think it should be working.
Yeah, I can hear you.
All right. I think it might be on your end, Don, but thanks for the heads up. Actually, Phil, you might need to text him that because he surely can't hear me saying that. All right. We're going to kick things off. Welcome, friends, to our webinar today, where we're going to be talking about how nitrogen creates yield drag, what the mechanisms are for that, and that contribute to that. There is so much in this topic, and this conversation really has evolved out of the last 15 years of experience of working with a different type of nutrition management system, where we have one of the key principles that we've worked with in the way that we've managed nutrition at AEA is we want to have nutrition, we want to have plants absorbing nutrition from biology instead of from mineral or ionic sources of nutrients, soluble sources of nutrients. And over the last 15 years, we've observed lots of interesting things happen, that when plants begin absorbing bacterial proteins and amino acids and peptides directly from the soil profile, they begin expressing themselves differently. They begin behaving differently. And this has led to a lot of study, a lot of research, lots of efforts to try to connect the dots and understand what's happening and what's going on inside plant tissues. And this whole topic of nitrogen interactions with other nutrients is much broader and much deeper than we can get into in a 1 hour webinar. So I'm going to go provide an overview of the highlights of some of the big picture pieces as we understand them right now that really impact plant physiology and can dramatically increase crop yields once we start managing nitrogen differently. I've included a number of references and citations in the presentation, but there's many more things I'm going to talk about that I've probably missed including references for. If you want to dig deeper, I would suggest a first place starting point is to start with Marshner's Mineral Nutrition of Higher Plants. I'm going to grab my copy here. Many of you I'm sure have seen this or have heard me talk about it in the past. I was rereading it again yesterday and this morning in preparation for this article, and the chapter on nitrogen is just simply fascinating. But of course, we've learned lots of new things since this book was published. We've learned lots of new things around rhizophagy and how plants utilize nutrients inside their cells. In addition to this book, if there's a lot of bibliography to follow up on here, but I would also suggest Gerald Pollack's book, Cells, Gels, and the Engines of Life. And what was the other one that was in my mind? Oh, James White's papers on rhizophagy. So we're going to touch on a couple of those as we dive through this, but the short version is, when you think about nitrogen, the common frame of reference that everyone uses is, if you want more yield, you put on more nitrogen. We don't think about nitrogen creating a yield drag effect, but in fact it does, and it can be very significant. And so we have the topics I'll be talking about today are, at first glance, they may appear to be counterintuitive, but when you really dig in and understand what's going on behind them, they start making a lot of sense. So with that introduction, I'm just going to dive right in. There's a lot that there just simply wasn't enough room to include. So I'm going to try to move pretty quickly. And if you have any questions for me, type them into the Q&A box. I'm going to try to leave plenty of time for Q&A at the end and dig into any topics that you have or any questions that you have. I would only ask that you keep your questions focused to the topic on nitrogen and nitrogen interactions within plants and within soil biology and how to make the overall system work. Because given the depth of that topic of what we could talk about, I don't want to go too far off track from that. So with that, I'm going to dive into the screen share and let's talk about nitrogen creating yield drag. So, quick overview. I want to quickly touch on the nitrogen cycle and how it functions in soil and plant ecosystems as it's understood or misunderstood today. Briefly touch on rhizophagy and then give a quick overview on how nitrate creates yield drag. And this topic, because I soon discovered there's so much to this topic, I needed to cut things out. So this webinar is focused specifically on nitrate for the most part. We could have parallel conversations about ammonium and about other forms of nitrogen, but we're really laser focusing in on nitrate because it is the form of nitrogen that has the greatest yield drag effect by far. And secondly, it's the form of nitrogen that is most commonly absorbed in highest proportion by most crops. And I'll expand on that in a bit here. Then I'll want to describe just quickly how microbial proteins increase yields and do not have a yield drag effect. And then how, as you're managing the transition, whatever your current nitrogen management protocol may be, how do you get to a place where nitrogen doesn't cause a yield drag, but does in fact give you the yield increase that you're looking for and that you're expecting. So when we look at the nitrogen cycle, you've all seen diagrams similar to this, I'm sure, that describes the overarching nitrogen cycle as it's moved into the soil through nitrogen fixation process by different types of nitrogen fixing bacteria, rhizobium and azotobacter and so forth, and then goes through the nitrification process where it switches from reduced forms to oxidized forms of nitrogen, which is specifically ends up as being nitrate. And this diagram as it exists here is slightly incomplete. This is one of the better nitrogen cycle diagrams that I've found online. But what is missing is it doesn't yet include the plant's capacity to absorb bacterial nitrogen or to absorb entire bacterial cells as described by the rhizophagy process by Dr. James White. So that's an important clarification, important distinction that I want to make, that this nitrogen cycle, while quite thorough, is still missing the rhizophagy component. And by the way, that's also why when I talk about this book, Mineral Nutrition of Higher Plants, the rhizophagy cycle is also missing from this currently described understanding of plant absorption of nutrients. So the rhizophagy cycle, I really wish we could be live and I could see you in person so that I could ask for a show of hands of how many people haven't heard of the rhizophagy cycle. I've been talking about this for the last couple of years. It's become much more widely known. So what I'll just describe briefly, we'll just say briefly, is that Dr. James White at Rutgers University, along with a number of his colleagues, have described how plants can absorb nitrogen or absorb nutrients generally from bacterial cells, where they are absorbing entire bacteria, moving them throughout the plant's vascular tissue, and the plant cells are absorbing these entire bacterial cells through various processes, but one is including a process called endocytosis. The short version is very simple. The summary is simple. The summary is that we can provide, I believe, this is not Dr. White's perspective or his endorsement, but what we've observed based on the field observations over a decade and a half now, we believe that plants can absorb the majority of their nitrogen requirement and their total nutrient requirement through this rhizophagy process. And when I say the majority, I'm talking upwards of 90%. So it's true that in a functioning, living bacterial soil and fungal soil where you have vigorous microbial populations, you will always have tiny trace amounts of nitrate and ammonium. But in the healthiest soils, that's all that it will be. It will be a trace amount. It'll be less than 5% of the total nitrogen in the soil profile will be in the form of ammonium or nitrate. The majority is contained inside bacterial cells and inside soil microbial populations. That's exactly where we want it, because in this form, it's not water soluble, it doesn't leach, and it's available for plants to absorb even when you have drought stress, when you have limited water. So I am really excited about the discovery or the elucidation, the description of the rhizophagy cycle that Dr. White and his colleagues have described. I've had him on the podcast. He's done a couple of webinars. There's lots more information available online around this process. But the bottom line for the purpose of this webinar is that it's possible to supply upwards of 90% of a crop's nitrogen requirement using this process, and that is how you will consistently produce the highest yields and the highest quality. Once this starts happening, when I say the highest yields, I'm not talking about a 2% or a 3% yield increase. What we have observed are significant yield increases once plants start getting nutrition from this process. So this is the ultimate end goal. And I want to describe a bit at the end of this webinar how we achieve that and how we get to that end goal. When we look at the energy requirements, I just find this intriguing that if we want to, for commercial ammonia fixation, the Haber-Bosch process is operating at 500 degrees Celsius under tremendous pressures. And it's interesting that bacterial enzymes can synthesize these same and can also fix nitrogen, but at common temperatures and pressures. It's fascinating the tremendous energy that can be focused through these bacterial processes. One of the key pieces is if we want to have the rhizophagy cycle functional and capable of supplying a significant amount of the crop's nitrogen requirement, we must have good gas exchange throughout the soil profile. The soil has to be able to breathe, has to be able to inhale atmospheric air that contains 70% oxygen and exhale air that has 20 to 30,000 parts per million CO2 for green plants to absorb. Without that natural inhaling and exhaling, you can't maintain the quantity, a large enough population of bacteria to fix enough nitrogen to supply what the crop's requirements are. So here's a quick overview of the different oxidation states of mineral nitrogen or chemical nitrogen, all the way from ammonium on the left, going through to nitrate on the right. And we can see lower left, lower right, you have the reduced versus the oxidized forms, which is something I've been speaking about quite a bit over the last couple of years. But the point that I want to make, and the reason I put this up here, is to illustrate why we should not be just talking about nitrogen. In addition, this is the mineral forms of nitrogen, but then you also have amino acids, amino sugars, peptides, proteins, bacterial cells, urea and amine nitrogen. You have all this array of organic forms of nitrogen, and plants can absorb the entire spectrum. However, the form of nitrogen that they absorb has a significant impact on that plant's future performance. So one of the things that we've observed, I had this experience when I was early days, just starting out doing consulting work, probably 12 or 13 years ago, working with a watermelon farmer in Texas. And we had put together a nutritional protocol. This was, in fact, I think before we had AEA products. And so we were using industry products that were available in the marketplace. And early on in the season, once we got to the bloom period, or even shortly after the bloom period, once we have tennis ball sized fruit, the grower was just freaking out about how small the plants were. The plastic wasn't even covered yet, and we already had tennis ball sized fruit. And the concern was that we didn't have enough vegetation, didn't have enough leaf surface area in order to produce enough fruit and to produce a large fruit. Well, that was not what happened. That crop, which never, even when it was fully mature, when we went through harvesting, there was still visible plastic, a lot of visible plastic. I'd say we had some in the neighborhood of 65 to 70% coverage of the plastic at that point. That was the highest yielding watermelon crop that farmer had ever produced up to that point, and still is amongst his top yields on the farm today. And I've experienced this phenomena over and over again. Specifically, now I need to make some distinctions here. There's three different crop types in the way that crops express themselves. You have a vegetative crop, let's say alfalfa or spinach or kale. You have what we call a single fruiting crop, which would be small grains or corn, for example, where all the blossoming and pollination happens in a very condensed window of time, in a matter of a few days or a week at most. And then you have the extended, or what I call the multi-fruiting crops, which would be like watermelons and tomatoes, where you have blossoming and pollination for an extended period of a couple of weeks or maybe a month. And it's this last group that I'm talking most about for this particular example. This group of crops, which blossoms and pollinates for an extended window, soybeans would be in this group as well. You will often find the highest yielding crops have the least vegetative biomass. Why is that true? It's true because usually what we have come to perceive as common and normal for these types of crops is excessive vegetative growth triggered specifically by nitrate that reduces reproduction. So this watermelon field, even though it had a relatively small amount of vegetation based on the farmer's historical experience, it had enough leaf surface area to fill a lot of fruit, and these plants had really strong reproduction. Trying to recall now, I think we harvested an average of 3.2 melons per plant on that field, which was 50% above the historical norms. So, how does nitrate create yield drag? 5 points, or maybe 6 here. First, excessive vegetation. It increases the crop's water requirements significantly, as I want to point out. It drains a plant's energy, which is counterintuitive. We're used to thinking about putting on nitrogen, we get this tremendous surge of plant growth. So it increases plant energy, right? In fact, it doesn't do that. It drains a plant of energy. I'll describe why. It reduces nutrient absorption. Here's an interesting one to think about. It increases disease, and it creates a pronounced tendency towards premature death. So let's unwrap each of these. Let's talk about the water requirement as a jumping off place. There is a tremendous amount of water required for the plant when it absorbs nitrogen for two reasons. The first is that when plants absorb nitrogen and they convert that, it's difficult to speak in generalities here because there's variation between different plant species, but broadly speaking, most agricultural crops convert the majority of their nitrate in the upper parts of the plant, in the vegetative parts of the plant, not in the root system. And so you get nitrate being absorbed from the roots and from the soil water, moving up into the leaves, and the conversion process happens in the leaves from nitrate to amine nitrogen, then to amino acids and proteins and so forth. And the initial steps in the nitrate conversion process to amine nitrogen require a lot of water. It takes 3 molecules of water for every molecule of nitrogen or of nitrate that the plant absorbs. And in addition to that, when the plant is absorbing nitrate and it's moving into the upper parts of the plant and being stored in the vacuoles inside the cells, it also creates weak watery cells, which lead to all kinds of problems, including increased transpiration. So it takes more water because the plant loses water more easily. The elevated levels of nitrate reduce the plant's ability to control the stomata and the plant starts losing a lot more water. So the short version is, if you give plants nitrate, if plants absorb a lot of their nitrogen in the form of nitrate, it's going to greatly increase the plant's water requirement. Let's look at what happens when plants absorb nitrate. Let's look at what happens in the rhizosphere. So this is the first paragraph is a direct quote from this book, Mineral Nutrition of Higher Plants, a direct reference. It says, as ammonium or nitrate comprises about 80% of the total cations or anions taken up by the plant. And I suspect, it's not stated in this reference, but I suspect it's referring to 80% of the atomic weight or of the molecular weight, because obviously in terms of actual numbers, probably wouldn't be that high. It has a strong impact on the uptake of other cations and anions, on cellular pH regulation, and on rhizosphere pH. Now, why would the form of nitrogen influence rhizosphere pH? Because when the plant absorbs either ammonium or nitrate, for one of them it releases a proton, and for the other it gains protons. So simple way to say it is to say that when plants absorb ammonium, it acidifies the pH in the rhizosphere. So you will drop the pH right around the root system, and you can take a soil that has a pH of 7, 5, or 8, that's very alkaline, and you can have a rhizosphere pH of 3.5 to 4, which is very valuable for increasing nutrient availability. So you can get a lot of calcium availability and trace mineral availability in these acidic soils right around the rhizosphere. However, when the plant absorbs nitrate, the opposite happens. And this is such a fundamental common problem across so much of agriculture, is that when you have, now let's say you have a soil that appears to have a functional and a well-balanced bulk soil pH, it's 6.2 to 6.4, somewhere in that range, and you would think the soil biology and everything is working really well. When nitrogen fertilizers are applied to such a soil, and they go through the nitrification process, the plant ends up absorbing the majority of its nitrogen in the form of nitrate. You can actually have an alkali zone in the rhizosphere where soil pHs are upwards of 7.5, as high as 8 or greater. And you can imagine, well, maybe you can't, that has a tremendous negative impact on the plant's ability to absorb other nutrients. When this happens, when plants are absorbing lots of nitrate from the soil, that means they will do a very poor job of absorbing calcium. They'll do a very poor job of absorbing manganese, copper, iron, cobalt, zinc to some degree, and boron. So there's all these trace minerals, silicon, there's other elements that are involved here as well. But the short version is simple. We can simply say that when plants absorb nitrate nitrogen, it alkalizes the rhizosphere pH and greatly reduces the plant's ability to absorb other nutrients. So if you want to create a plant, in society at large here, I believe many of you that are here and that listen to the content that we've put out historically, when we look at public health and the challenges that are present in our population throughout North America and to some degree in all of Western civilizations, but particularly here in North America, we have a problem that many people have full bellies and are starving. They do not have, when I say they're starving for good nutrition. We have a lot of empty carbohydrates. We have an abundance of carbohydrates, but not good nutrition to go with it. And so we have an obesity epidemic and all these challenges with degenerative illnesses like heart disease and diabetes and stroke and cancer. The list goes on and on. If you want to create a plant like that, you feed it nitrate. Nitrate for plants is the equivalent of empty carbohydrates for people. You get lush vegetative growth, lots of biomass, but without good nutrition, without proper nutrients, without the proper minerals that plant needs for it to be healthy. So this has been well understood for decades. This is not new information, but it's just surprising to me that it's not more widely discussed and talked about. Nitrate produces weak cells and weak cell membranes. So fundamentally, it is weak cell membranes that are one of the foundational requirements. When we talk about the disease triangle, there's three components of the disease triangle. There is a potential pathogen, a susceptible host, and a proper environment. We don't give enough consideration to what is the definition of a susceptible host. A susceptible host is not just a random tomato plant, because we know that some tomato plants are resistant to one disease and other tomato plants of a different variety are susceptible to the disease. So what defines a susceptible host is partially the terrain, the internal construction, and the nutritional integrity and the microbiome integrity of that plant. And weak cell membranes are one of the fundamentals that define a susceptible host for many, many different diseases. So often when we have bacterial infections and fungal infections, some types of viruses, we find that we have weak watery cell membranes from excessive nitrate application. And this is also the foundation of why some crops die down early, or they die prematurely. If you have a potato crop that has excessive levels of nitrate, that potato crop will become infected with verticillium and it'll die down when the potatoes have barely reached the mature stage of and the final harvest, or the final harvest size that you want to harvest. If they don't have excessive nitrates, they often will not contract verticillium and they'll stay green and continue to grow right up until frost. So this is a difference between how plants will express themselves differently based on whether they're absorbing nitrogen in the form of nitrate or other forms of nitrogen like urea and ammonium or bacterial proteins. And then I think many of you are also aware that when you have weak watery cells, those are the foundation of most fruit storage problems. So if you have storage problems with or calcium deficiency problems like blossom end rot and corking and bitter pit, those are fundamentally weak watery cells. And you think about those diseases I just mentioned. I named blossom end rot and corking and bitter pit. Those are commonly thought of as being calcium deficiencies. But think about this. What if the calcium deficiency is being caused by root absorption of nitrate, increasing rhizosphere pH and making it difficult for the plant to pick up calcium? What if the calcium deficiency isn't caused by calcium being low in the soil, but by nitrate being high in the soil? This is a common phenomenon. It's one that we see all the time. So now let's talk about the next point. Nitrogen creating an energy drain. Like, why would nitrogen drain energy from a plant? This is another citation. Actually, it might be from an earlier edition of Marshner's, Horst Marshner's Mineral Nutrition of Higher Plants. I think it might have been in the second edition where I read that a citation that indicated when a corn crop absorbs 80% of its total nitrogen requirement in the form of nitrate, that will consume 16% of that plant's total photosynthetic energy just to convert nitrate to proteins. Or actually, to say that correctly, just to convert nitrate to amine nitrogen. That's a tremendous energy drain. 80% of nitrate absorption, or 80% of total nitrogen as nitrate, which is very common. That's what happens in most production agriculture. Might even be greater than 80% in many cases. It takes 16% of a plant's total photosynthetic energy. Why does it drain that much energy from the plant? Because the energy requirement, the sugar energy, the photosynthate energy that is needed to convert nitrate to amine nitrogen is really high. So here's a couple of citations and references. Again, these are direct quotes from the book that I showed you just a moment ago. So when we think of it in ATP equivalents, I missed finding the math for sugar and carbohydrate requirements. But the energy requirement for the reduction of 1 molecule or 1 mole of nitrate is 15 moles ATP, with an additional 5 moles for ammonium assimilation. And this reference, it was speaking specifically to when nitrate assimilation happens in the root system. Ideally, nitrate assimilation should happen in the leaves And when that happens, it will require less energy. Less energy is required to convert nitrate in the leaves than it is required to convert nitrate in the roots. However, many agricultural crops under mainstream agronomic practices convert a lot of nitrate in the roots rather than the leaves. Why? Because they get too much and the leaves can't keep up. So, short version, bottom line is, when there's this common phenomena when growers switch to organic production, or when they foliar apply nitrogen, it's commonly understood that when we put on a foliar application of urea versus a soil application of urea, we require a lot fewer pounds per acre to produce the same crop response. Or when a grower switches and becomes organically certified, they'll start using organic forms of nitrogen such as liquid fish or amino acids, corn steep liquor, different types of materials. And all of a sudden, instead of using 1.5 pounds or 1.25 pounds of nitrogen to grow a bushel of grain, they might be using 0.7 pounds of nitrogen or 0.5 pounds of nitrogen to grow a bushel of grain. And this has been observed commonly, widely understood to occur for decades. And this is the difference. A unit of nitrogen is not the same from a plant response. When plants absorb amino acid nitrogen, it actually gives them energy. They gain energy from amino acids. They gain energy from bacterial protein. But when they absorb nitrate, it costs them energy. This is why why different forms of nitrogen have different levels of efficiency, and it takes more. If the plant is getting all its nitrogen from nitrate, as it is in most of mainstream agronomy, it's going to take higher levels. It's going to take that 1.25, 1.5 bushels of nitrogen per bushel of grain. But if it's getting amino acid or peptide or protein nitrogen, it takes a fraction of that because it's not depriving the plant of energy. Anyway, yeah, I'm going to move on. There's more that I could talk about here, but this is the key piece. So I spoke earlier about the increased water requirement. This is just from field experience and observation. I can't point to a citation on this, and it varies based on crop species and local context. The local context is important here. But what we've observed is that when plants get the majority of their nitrogen from nitrate, it increases the plant's water requirements. We think somewhere between 20 and 30%. Some crops more, other crops less. And this is as compared to plants who are getting most of their nitrogen from the rhizophagy cycle. So as I pointed out, this is because of two key drivers. As well, there's a couple of other drivers that we think are relevant as well, but the big ones are that there's no water needed to convert nitrate, or less water, I should say, and less water required because you have stronger cell membranes and you have less transpiration. And another factor that happens, I described this in my webinar on the plant health pyramid, when you have plants absorbing most of their nitrogen from microbes, from bacterial cells, and they have this energy gain, that energy gain expresses itself as this strong, waxy, oily coating on the leaf surface, and that helps the plants cool a lot more efficiently. The short version is, there's a number of different mechanisms. We don't pretend to fully understand it. We think we have a handle on a couple of them. But the bottom line is you can greatly increase a crop's drought resilience and reduce its water requirement by making sure that it gets nitrogen in forms other than nitrate. And of course, this is one of the reasons why in drought-stressed years, in dry areas, the farmers who are using cover crops or who are supplying nitrogen in forms other than nitrate, whether that's from manure, compost, whatever the source might be, those crops consistently perform better in drier conditions because they have less water requirements. And they can continue to some degree, in the case of the rhizophagy cycle, they can continue to access nutrients even in the absence of free soil moisture. So this is a photo of a page that was shared from one of the colleagues that I've worked with, a farmer grower who's been on these webinars in the past. And this was research that was assembled. This was a review of the literature that was done by an agronomist at Cal Agri, if I recall correctly. And he described that in his literature review, he found that a foliar application of a pound of nitrogen was the equivalent of 7 pounds of nitrogen applied to the soil. And it's pretty remarkable when you think about this. We see this effect commonly. Now, there are many critiques of this type of approach to say, well, we've done the research and we haven't really been able to see or to find these equivalencies, observe these equivalencies in the field practice. And I have reviewed the reviewers, I've reviewed the critiques of those people who weren't able to find success, and it's blatantly obvious what they're getting wrong. It's timing. You wouldn't consider putting on 50 units of nitrogen foliar applied when you have a corn crop that's at V3 or V4 or V5, when the majority of the needs are later. But that's exactly what researchers are doing to try to discredit this. So it's really a question of optimal timing when we're looking at foliar applications. So I'm going to go through a few specific crop examples. The minutes keep ticking by pretty quickly here, but I want to give you a few quick crop examples of how nitrogen creates yield drag. And actually, well, I'll get to this point on vegetation yet in a bit here. So when we look at corn and the formation of black layer, we know that every day that we can delay the formation of black layer gives us an additional 4 bushels per acre yield. So if we can extend the grain fill period and delay black layer and push that back, that we can have a significant yield response really quickly. And so the question is, what causes black layer and what is black layer? I had a conversation with Michael McNeil probably, I don't know, half a dozen years, maybe a decade ago, where he was describing that what causes the black layer, of course, is that we have placental cells collapsing and blocking sugar transport into the kernel. And black layer can also be caused by photosynthesis of the plant itself just slowing down or shutting down. When you have defoliation, some of the research that has been done around defoliation, basically what happens, anything that limits sugar movement into the kernel is going to trigger the formation of black layer. But one of the triggers that McNeil and colleagues identified a decade ago was when you have weak cell membranes, because those cells don't have enough calcium and don't have enough silicon, you will get early collapse of those placental cells. And that abundant calcium and silicon nutrition will delay that the collapse of those cell membranes and delay the black layer formation. So when you think about what I said earlier about nitrate, it's quite common for plants who are absorbing nitrate to not do a good job of absorbing calcium, which leads to weak cells and which leads to the early formation of black layer in corn. This is one of several different mechanisms by which plants absorbing excessive levels of nitrate will lead to premature senescence, premature development of black layer. Here's one on mold and mycotoxins. This is a very simple trial that was run, I don't know, it's also 10 or 12 years ago, when we were doing product testing and early research and development on our humicarb product. So left 3 leaves and corn ears were treated with humicarb. The right was untreated. It's a pretty remarkable difference in the field. And you can see the tip fill, and there's quite a difference here in the ears as well. But these samples were collected with the intention of sending them to a laboratory. This was pre-harvest. There's still fairly high moisture content. I want to say there's somewhere in the neighborhood of 22 to 23%. And so the intention was to ship these ear samples off to a lab. Well, they ended up sitting on a desk for a week, and this is what they looked like. So the only difference was 3% humicarb applied in 3 gallons per acre 1034-0 in the furrow outplanting. Nitrogen was side dressed later, but one of the effects that we know of from humicarb applications is that it's very effective at stimulating biology to rapidly convert nitrogen, applied nitrogen, into bacterial proteins. So I don't have the data for this slide deck, but one of the data points, or several of the data points that we have on this trial, indicate that the crop leaves had much lower levels of nitrate. And of course, we weren't able to check the grain for nitrate versus different forms of proteins or different nitrogen forms. But the bottom line is that reduction in nitrate had a significant reduction, produced a significant reduction in molds on the year after when it was stored inside a plastic bag. And we've observed this just over and over again, where we see reductions in molds and mycotoxins and aflatoxins. 2012, we had a major reduction in aflatoxins on the growers that we were working with over what they experienced in untreated fields. When we look at lodging, short version is that plants that are absorbing nitrate do a poor job of absorbing copper and calcium. Copper in particular gives, so we have the effect of weak watery cells and weakened cell membranes and reduced copper levels, which reduces lignification. We very commonly, when we have growers that where crops experience wind stress, we have a lot less lodging when we start managing nitrogen differently and nutrition management differently. Storability. This is for potatoes and onions and apples, any fruit or vegetable that spends an extended period of time in storage. You know, profitability is not just about yield so much as it is about marketable yield. And what defines marketable yield is the fruit or the vegetable that actually gets sent to the retail store shelf or to the end user, whatever that might be. And we can easily, mainstream agronomy can fairly easily produce lots of yield per acre that doesn't store really well, and particularly in regards to the way that nitrogen is managed. So what happened? I'm missing a slide, unfortunately. But what happens is when you have, well, going back to my earlier comments around calcium absorption, we know that if you have purple blotch or ring spot or any of this long list of disorders that can occur inside an onion or inside a potato, those are very frequently linked back to calcium nutrition. But we need to stop thinking about calcium nutrition in isolation from potassium and nitrogen management. When you have too much potassium and too much nitrate, it will greatly inhibit plants' ability to absorb calcium. So, and many of these challenges fundamentally come down to calcium and trace mineral nutrition. So, would be interesting to talk a bit about wheat, because we know that it's fairly common for wheat to be compensated or to get premiums based on protein content. There's quite a bit of interesting research out there on protein, how protein content responds to applications of nitrogen at different stages of plant life, foliar applications at later stages versus earlier stages. But here's the interesting story around protein. Well, first of all, we can say there's lots of variation. And it's generally true that there isn't much correlation between nitrogen applications to the soil. I'm not talking about foliars here, but nitrogen applications to the soil and grain protein content. And there's a number of reasons for why that is, but the short version is that nitrogen applied to the soil often converts to nitrate, moves into the plants, and isn't properly converted to storable proteins. So when you have, and it's not converted to storable proteins because the plant doesn't have enough magnesium, sulfur, and molybdenum. It's those three elements in particular. There is a much closer correlation. In fact, there's a very close correlation between sufficiency of those three nutrients and protein content than there is between nitrogen in the leaf and protein content. And here's why. When the plant absorbs nitrate during the vegetative growth stage, it will store that nitrate in the vacuoles inside the cells. And so you can pull a tissue analysis or plant sap analysis that shows you have high levels of nitrate, and therefore you don't need to apply more nitrogen to have a high protein crop. But the plant, as I understand it, will attempt to only transfer proteins into the grain, not nitrogen or not nitrate. And for that reason, if you have abundant nitrate but not enough magnesium, sulfur, molybdenum, a lot of that nitrogen is going to remain inside the leaf and not move into the grain effectively. Another consideration, I shouldn't say that it's not going to move into the grain at all, because it will to some degree, which brings us to another deception. This is another conversation, but when you send grain to a laboratory to be analyzed, they don't measure protein. Many of you are aware of this, I'm sure, but they measure nitrogen, and they multiply it by a mathematical factor, usually by 6.25, to extrapolate protein. So it's a projected protein number. It's not an actual, real, measured protein number. It's a measured nitrogen number. You can inflate that artificially by just simply putting on a large application of foliar nitrogen like urea late in the growing season and have it immediately moved into the kernel and into the grain before the plant can fully metabolize it. So anyway, there's a whole bunch that we could unwrap and unravel there around protein content in wheat, because it's measured there, but it holds true for all grain generally across the board. So the clock keeps ticking here. Wow, way too fast. I see we've got lots of questions. I'm going to speed through a couple of these last really important points. I came up with this diagram to describe how I observed plant growth energy. So thinking about the energy inside the plant, you have two forms of energy. On the left side, you have vegetative energy and you have reproductive energy. And you want those two to constantly be balanced. And balance might mean something different than what we're used to seeing in the case of the watermelon crop that I described at the beginning of this webinar. So when those two are balanced, you will get really strong reproduction and you don't have excessive vegetative growth. And then you have all these other factors that can contribute yield drag. Yield drag could be drought stress. It could be temperature, too hot temperatures or too cold temperatures. There's all kinds of things, external influences that can contribute to yield drag. But there's also many agronomic influences that can contribute yield drag, like plant growth regulators, or like excessive nitrate, or excessive chloride, or excessive potassium. I've described some of the mechanisms. There's more, but I've described some of the mechanisms by which nitrate can create a yield drag. So when we look at these nutrients, calcium, potassium, chloride, and nitrate, as well as auxins, drive vegetative growth energy. And 3 out of the 5 can exhibit a yield drag effect when they're present in excess. And I should maybe clarify that language. When I say they are present in excess, what I mean is that they are present in amounts larger than are required for optimal plant health and yields. And this might surprise you, but if you base it on that definition, that includes greater than 90% of agriculturally produced crops, because we commonly apply too much nitrogen too early, and by the time the plant gets to the grain fill or fruit fill period, or the period of the crop stage where we have peak nitrogen demand, the majority of the nitrogen will usually have converted to nitrate in the soil profile. And I've described some of the mechanisms by which nitrogen creates yield drag. So let's just elaborate or follow up on a few of these thoughts. Nitrate creates yield drag by 1, creating excessive vegetative growth, which corresponds to fewer buds, flowers, fruit, grain. 2, it increases the plant's water requirements, which limits yields, particularly when the crop is challenged with moisture. You know, it used to be throughout the grain belt in the Midwest, their soils and their crop, their corn production practices, they were quite comfortable going for a 3-week period without rain. And I have this from Michael McNeil and Don Huber and many older, much more experienced and longer life experienced agronomists than I. The standard rule of thumb was that they would be comfortable for 3 weeks without rain. Today, the moment we go a week without an inch of rain, or longer than a week without an inch of rain, crops start experiencing moisture stress. What is different? What's changed over the last 30 some years or longer? One of the changes that has happened is we put on a lot more nitrogen than we used to, and we've lost a lot more soil carbon than we used to have. So there's a number of contributing factors, but there's no question in my mind that the increased water requirement as a result of a lot of nitrogen application being converted to nitrate is one of the major contributing factors for the increased water requirement. Photosynthetic energy, sugar energy needed for nitrate conversion. And that means that energy, when you think about converting nitrates, absorbing 16% of a plant's total photosynthetic energy, and the fact that 100% of that 16% could be gained back by the plant absorbing microbial proteins, that means theoretically you've got a 16% energy jump that can go directly into yield. Will that translate to a 16% yield increase? Based on our field experience, that's not unrealistic at all. So there's the summary. Vegetative growth, water requirements. Actually, I'm going to add 2 more pieces here that I missed. Reducing absorption of calcium and trace minerals, and premature plant death. Premature plant death. This is the difference between die down and dry down. A really healthy corn plant, I know I've been using corn as an example, but other crops as well. A really healthy corn plant will have a high moisture stalk with a minimum of 4 green leaves below the ear and green all the way to the top, and an ear with the grain at 17 to 18% moisture content. That used to be normal. That's a definition of proper maturity and proper dry down. Today, what we consider normal is plants who die down. They die prematurely. So you end up with a low moisture stalk, a plant that has moved all of its energy, sucked all the energy out of the leaves from both the top down and from the bottom up and moved them together into the ear. And the plant is dying early, and you have a dry plant, dry stalk and leaves with a high moisture content ear, 25 to 30% moisture content or 20+% moisture content. That's the difference between die down and dry down. But in addition to yield drag for a specific crop, we also have ecosystem level long-term yield drag. And what happens with these elevated nitrogen applications is we prevent the soil from building soil carbon levels, and we prevent soil from building microbial nitrogen reserves. We have an abundance of examples today, and more than enough farms who have experienced this, who've been through this transition pathway, where they now have soils that have high levels of nitrogen contained inside the bacterial population. Nitrogen that doesn't leach, nitrogen that's available in a drought. They don't need to continue applying nitrogen. In fact, many of these farms are down to less than 20% of their historical nitrogen applications. And you can't build nitrogen levels in soil and hold it stable as long as we continue to have these high nitrate application levels or high nitrogen application levels. It's self-fulfilling destruction, or creating a drug addict, or whatever you want to call it. So when we think about nitrogen timing, it's very important when we are taking, as we start going through the transition, one of the easy, fundamental first steps is you apply nitrogen when the crop needs it, not months in advance or weeks in advance. Because when we apply nitrogen close to the root system, long before the crop needs it, it shuts down this rhizophagy process. It shuts down the bacterial populations. And you, in essence, create a drug addict. You make sure that the nitrogen cycling process can't function in soils because you've added too much nitrogen from the very beginning. And by the way, this can happen not just with quote unquote chemical nitrogen like UAN or urea, but it can also come from over applications of manure, liquid manure in particular, but also from dry manure applications in large amounts. Don't really see it happening from cover crops and cover crop incorporation because of the bacterial population that's already associated with those, but it can definitely come from manure applications. So our approach to nitrogen management is pretty simple. Give plants what they need only when they need it. And we use soil analysis and sap analysis to determine that. We do not guess. And that's why, since we don't have to guess, we are able to produce consistent yields, higher yields than what are expected in the region, and not fall on our face very frequently. For foliar applications, we prefer amino acids or low biurea. And for side dress, if we're in a situation where we do need to side dress, our preference is urea, and include with the urea the nitrogen efficiency program, which many of you have heard me talk about. The nitrogen efficiency program is essentially these three pieces with sulfur. So we're using humicarb at 3% of the total solution, rejuvenate at 3% of the total nitrogen solution, plus rebound molybdenum at a pint per acre, and sulfur, usually using ammonium thiosulfate, so that we achieve a 10-to-1 nitrogen to sulfur ratio for whatever source of nitrogen that we're applying. And we conducted our own in-house research. I think this was this most recent year. We found that a straight urea application lost 16% more nitrogen, or not 16%, 16 times more nitrogen to leaching than when we combined the nitrogen efficiency program with the urea. That's pretty impressive. One of the goals that we've stated is that we want to have the nitrogen efficiency program, the purpose and the intent of that is to stimulate bacterial populations so that 100% of the applied nitrogen is immediately converted into and absorbed by bacteria, accumulated inside bacterial cells, and converted to bacterial proteins, because then we save it. It doesn't leach, it's available in drought, and the plants can still continue to absorb it. So if you have any further questions, now's the time to type them into the chat box. Oh my goodness, I see that we have 50 questions and we're already up on the hour. I apologize for taking as much time as I have. I knew there was a lot. I wanted to get through it quickly, but I am going to take the time to answer all the questions. So I'll try to be concise, make it to the point, and move quickly. But if you have questions, if you're willing to hang around, I'm sure the conversation is going to continue to be interesting. And if you want to learn more, if you want to talk specifics, I've spoken in very broad generalities. If you want to talk specifics about your operation, our team would love to talk to you. Reach out to us, call us. I'm available on the phone as well as a backup. If you have questions our team doesn't know the answers to, which doesn't happen very often, but I'm happy to connect with you. I really enjoy the interaction, enjoy these conversations. First question is from John Warmerdam. Hi, John. You've shared that nitrate is a vegetative nutrient and fruit fill is a vegetative process. Is there a place to apply nitrates after the cell division phase on tree crops? It's an interesting question, John. You could do that if you're concerned about fruit being too small and not filling properly. But in most cases, you're likely to get a better response from an amino acid or a peptide application or a protein application of some type than you would from a nitrate application, would be my guess. Question from Justice. Why are AEA nitrogen plant sap analysis target values higher than NCC target values? Justin, I don't know what crops you're referring to, so I can't say specifically, but in general, I can say that we've optimized our values based on where we get the greatest level of disease and insect resistance combined with the highest yield. So what you're likely to find is that not only do we have total nitrogen requirements that are higher for some crops, but those also correspond with higher levels of calcium, for example, or higher levels of silicon to balance that out. A follow-up question from Justice: can you comment if total nitrogen in plant sap is twice as high as recommended, do all other nutrients have to be doubled to reach optimal levels? No. It's much safer and much wiser to try to bring the nitrogen levels down. And the reason I say no is because if you just try to double all the cations and the anions, what's going to end up happening is you end up with imbalanced pHs in the plant sap, which is going to lead to disease susceptibility. So you're better off to try to balance mineral profiles at a lesser rate than double of whatever the optimals might be. Question from Terry: do you still use nitrate soil tests to monitor nitrogen that is available for crop growth? It's a great question, Terry. We use the Haney analysis, usually through Ward Labs or through Regen Ag Labs, that measures not just nitrate, but measures different components and different fractions of nitrogen that are in the soil profile. I know there's other growers that are also experimenting with the Illinois nitrogen test that's been popularized by Richard Mulvaney, and which has many similarities, I would say, to the Haney analysis. It's different in some ways, but you can listen to my podcast interview with Rick Mulvaney regarding that. Next question from Melita: if we use molasses as a food source for microorganisms in order to create amino sugars, what are the optimal doses without the plant becoming dependent? The answer to that is going to depend on how much nitrogen you've added to your system. So it could be as few as, so first of all, I would say that the goal is not to add, you shouldn't strive to add enough sugar to balance out the carbon to nitrogen ratio. That's going to be prohibitively expensive and shouldn't be necessary in most soils. Instead, the goal is just to add enough sugar to jumpstart or to really accelerate the bacterial populations, which would usually be an application in the neighborhood of a few pounds per acre. This is why we include Rejuvenate, or one of the reasons why we include Rejuvenate in our nitrogen efficiency program, and it would add sugars at only a rate of a pound or two per acre, but of course it has lots of other stuff in there as well. Question from Terry: tissue or sap tests, what levels of nitrogen do you like to see in a corn plant at V4 and R2? We no longer use tissue analysis. We exclusively use sap analysis, and we just completed, actually not just recently, but it's been a bit ago that we completed our most recent database analysis and looking at where the highest crops were performing. So I can't answer that question for you right off the top of my head, Terry, but I'd be happy for you to connect with the AEA team and give you specific answers on what we're looking for in sap analysis at those specific crop stages. Question from Darren: the form of nitrogen taken up affects soil pH. Does soil pH affect the soil nitrogen cycle and the form of nitrogen in the soil? My thoughts go to bacterial glues that I recall being alkaline. So is the fungal to bacterial ratio important for soil nitrogen form? Darren, there's a couple of questions wrapped up in your question there. And to some degree, you're asking the right question. It's a bit of a chicken and egg question. Does soil biology determine pH, or does that affects nutrient availability, or does the soil chemistry affect the pH that determines the biological population that determines nutrient availability? Maybe it's more like the house that Jack built instead of a chicken and egg. But anyway, the short version is that yes, fungal to bacterial ratios do alter soil pH. And obviously soil mineral balance, calcium to magnesium ratios and other elements really affect soil pH. But if you're dealing with calcareous soils, if you're dealing with if you're dealing with oxidized soils, which is most agricultural soils, you will want to have the plants be absorbing nitrogen in the form of preferably urea, well, most preferably bacterial nitrogen, secondly urea, third ammonium. Avoid plants absorbing nitrate at all costs. This is going to have the effect of acidifying the rhizosphere and increasing nutrient availability. So the pathway to avoiding the absorption of nitrate at all costs is don't apply it too early. Because if you apply nitrogen to soil that is oxidized or to soil that is alkaline, that whatever form of nitrogen, if it's urea, if it's ammonium sulfate, if it's UAN 32 or 28, it's going to convert to nitrate nitrogen in a matter of days or weeks, depending on moisture and temperature and context. Question from Anne, does urea application change pH of the rhizosphere? So I just answered that. The key point is it's not the form that you apply, it's how long you apply it before it was absorbed by the plant and in what form it got transitioned to. It was included in my third slide. I was compressing stuff and I didn't really get into this in detail, but the short version is that when you apply urea or when you apply ammonium, it will go through the nitrification process and convert to nitrate in most agricultural soils because A, either they're alkaline, or B, they're oxidized, meaning they're tilled. They have application of limestone, tillage, too much oxygen, whatever might be the case, they will quickly convert to nitrate. That can happen in a week. It can happen in 4 to 5 weeks. Happens pretty quickly. Question from Tom. When you fertilize with ammonium, I just answered this question. Thank you, Tom. Glad to see you here. Question from Mr. Anonymous. Urea or calcium nitrate, which one has a more negative effect on soil biology? The better question, or the right answer is, it depends on how much you apply and whether it's been buffered. Both of those materials have a very high salt index, and you can buffer out the potential negativity by applying them with humic substances and with carbohydrates. Question from Jessica. In your opinion, what's the most accurate way to test nitrogen use efficiency of your plants? Jessica, it depends a bit on what crop you're talking about. Well, actually, I guess you could use this for most crops. I would propose you look at nitrogen application per unit of yield. So how much nitrogen is required in whatever form you're applying it in to grow 100 bushels of a certain crop or so many tons of potatoes. And that way you will actually be able to accurately track nitrogen efficiency over time. Question from Bryant, don't organic sources of nitrogen, for example amino acids, get converted to nitrate very quickly in the soil? I alluded to this earlier, Bryant, when I spoke about manure being converted to nitrate. The short answer is yes, they can. It depends, again, on the amount of carbon that is contained with them. So let's say ruminant manure like dairy manure or beef manure, this tends to happen more slowly because there's more carbon contained in that manure, whereas with hog manure or poultry manure, there's less carbon contained and they tend to convert to nitrate much more rapidly. Question from TB, curious about the nitrogen cycle of manure. Would banding manure right on a corn row be a negative or a positive? EPA frowns on broadcasting manure on top and to not incorporate. Would the cover crops help incorporate liquid manure in a no-till operation? Yes, TB, you're asking the right question. The best place to put a manure application is to put it on a living cover crop and have that cover crop quickly pick up that nitrogen and incorporate it inside the plant so that when it then goes back into the soil system, it's in the form of organic nitrogen rather than in the form of nitrates or ammonium. Question from Scott Gale, how does 28 or 32, hi Scott, how does 28 or 32% UAN play into this for the soil and plant? You have 3 different sources of N, and it's probably the #1 fertilizer in the US. Does the nitrate overrun the other 2? The short answer is yes, it does, because for 2 reasons. The way it's commonly applied is too early before the plant actually needs it. And since it's applied too early, the plant gets a shot of nitrate then, which is most available and most rapidly absorbed. And then the urea and the ammonium that's left converts to nitrate over a period of time. And then the plant gets an even further shot of nitrate. So I'm not a fan of 28 or 32. Lots of the growers that we work with use it, but I prefer liquid urea, and even for a side dress, and I prefer to apply it right when the crop needs it, or a week or so in advance. This is where you're going to get the greatest crop yield response. Question from Darren. I've been answering questions as fast as I can, and I'm still at 50. And I was at 50 when I started. What's your opinion on corn steep nitrogen, and what impact does it have on crops and rhizosphere biology? Corn steep nitrogen is generally in the amino acid form as I understand it, and it tends to have a positive impact on both plants and biology, and it requires fewer pounds of N, has greater N efficiency. Question on optimum dose of sugars with urea. I think I already answered that question. How do we measure bacterial nitrogen fraction in the soil with the Haney analysis that I referenced earlier? Question from Jason. If I'm applying 160 units of nitrogen as ammonium sulfate per acre in a blueberry production, granular and drip combination, what would you suspect I could back that off to if I applied urea foliar? Jason, very, very good question. Very important distinction. So you're growing blueberries. There are two crops that are adapted to, or two commercial crops that are adapted to do really well at absorbing ammonium. They are blueberries and rice. So you're using the right form of, of nitrogen. I would not suggest switching from ammonium sulfate to urea. Continue using ammonium sulfate because of the crop that you're growing. And I include this topic in my more in-depth seminars, but blueberries and rice are both adapted to thrive in very reduced environments. That's why they can thrive in saturated soils, and why they have such a shallow root system in the case of blueberries. So, but in my experience, the 160 units of nitrogen that you're applying is really high. I think you could safely do a lot less than that if you were managing that and buffering that out with sugar and other things. So we have some very high yielding blueberry growers that we work with that are less than half of the amount of nitrogen that you're applying. Actually, they're under 60 units. Question from Victor. Do I consider amino acids or peptides from fermented yeast or liquid fish as a bacterial protein? The short answer is yes. You could, the better, rather than saying bacterial proteins, I could be saying microbial proteins, but I'm just generically saying bacterial proteins because that represents the majority of what's in the soil profile. Question from Nick. Does ammonium nitrogen take more or less energy from the plant to convert in comparison to nitrogen? And how about urea nitrogen, and what percentage amounts? So Nick, I actually answered this question in some detail in, I have a webinar on YouTube on nitrogen use efficiency where I go into this. I was under the impression that ammonium takes less energy than nitrate, quite a bit less. And I still think that's the case, but I did find at least one citation, actually included in the slide deck here, that indicates that perhaps ammonium takes more than nitrate, but not as I understand it right now. So I need to double check on that. But the short answer is generally ammonium takes, as I understand it, ammonium takes a lot less energy to convert than nitrate does. Question from Sarah, can bacterially dominated soils with a pH above 7 convert ammonium applications to nitrate for the plant to take up? Yes, they can. In fact, it happens the fastest in alkaline soils and in oxidized soils. So even with no nitrate forms of nitrogen being applied, I have observed nitrate within the plant. Yes, that would be the case. We find, Sarah, this entire point I've been trying to make for this webinar is that most of the nitrogen absorbed by most commercially grown crops is in the form of nitrate, regardless of what form is applied, because of the condition that our soils are in and because of the condition that our soil bacterial populations are in. Question from Gord. Can you walk us through a program that can achieve 200 bushel corn crop with a small amount of nitrate absorption, forms of fertilizer, number of foliar passes, etc.? Gord, we've had a couple of webinars recently. I guess with the webinar that we had recently with Bo Clausen, we didn't really get into a whole lot of detail, but our team at AEA would be happy to walk you through the particulars. But in short, we typically apply no nitrogen at planting, and I'm talking about a corn crop here. So it's partially context dependent. It's soil dependent. We look at the Haney analysis, we see what's going on, and we don't guess. But here's what they frequently end up looking something like this. No nitrogen at planting because we want to get the rhizophagy process started. 10 to 20 to 40 units of nitrogen as a side dress at about V5, dependent again on context. And 1 or 2 foliar applications of nitrogen or irrigation applications of nitrogen if that's relevant during right around VT or R1, somewhere in there, depending on, again, context. Question from Mike. I'm farming 15 to 20-year-old almonds conventionally in the San Joaquin Valley. Trees are very vegetative and have primarily been farmed only injecting UAN32, sulfate of potash, and solubor. These trees have been farmed according to UC standards of applying 68 pounds of nitrogen per 1,000 pounds of nuts harvested. We are sap sampling this year and are aiming to be better stewards of nitrogen, also planning to water and run foliar amino acid chelated micros to help metabolize nitrogen. Do you recommend using soy protein hydrolysate amino acid nitrogen? Also, how do you compare amino acid nitrogen pound for pound with synthetic nitrogen? A couple of questions there, Mike. Yes, generally, I'm in favor of using soy protein hydrolysate. Seems to perform very well in lots of different situations. And we've found, this is crude rule of thumb based on experience, we've found that a pound of amino acid nitrogen seems to produce the same crop response as 4 pounds of nitrate. And you can verify, in fact, you should verify performance of everything that's going on with SAP analysis, which it sounds like you're already doing. So I wish you success in that. I'm sure you're going to have lots of fun figuring that out. And I mean that, I'm not joking. I think it's going to be very enjoyable because I think you're going to be very pleasantly surprised. What happens with excess urea that's applied to the soil? Answer is it gets converted to nitrate and then it leaches. Question from Justice, how much nitrogen requirement is possible to cover with foliar nutrition? Well, depends on the crop and, well, what I can say this way is it is possible to cover 100%, but is it economical? Is it desirable? I would say probably not. The goal should be to get the majority coming from soil biology and just correct deficiencies on a very limited basis with foliars. Question from Damon. During one of Dr. White's presentations, he mentioned the presence of nitrogen-fixing bacteria on the leaves of plants. Can you briefly explain how and why the bacteria would be in the leaves? I can't explain that briefly. I've got some pretty interesting books here behind me on bacterial populations in the phytosphere, on the phytoplane, as it's referred to. The short answer is that, as I understand it, bacteria on the leaf surface have a symbiotic relationship with plants exactly the same as bacteria, or maybe not exactly the same, but very similar as bacteria in the rhizosphere. They have a symbiotic relationship with the plants. The plants provide them with carbon, with sugars, with energy, and in turn, they protect the plant from potentially infectious diseases. They solubilize dust and minerals that land on the leaf surface and provide the plant with nutrition. So there's a symbiotic relationship that happens on the leaf surface, much the same as what happens in the rhizosphere. Question from Bruce. Would a foliar spray of ammonium sulfate, a late vegetative stage of growth on corn, be a good way to supply the nitrogen needs? It's okay, but urea, low biuret urea is going to be better. Question from Meletta. If we use fish hydrolysate as a source of amino acids, can we overdo it like nitrate? I haven't observed that yet, actually. stop to think of it, I don't think I've ever observed, like, what is excessive levels of amino acids? Like, I've never observed really elevated levels of nitrogen on a sap analysis coming from amino acids. What happens is you will get supersized plants very quickly with amino acids, much more quickly than you will with nitrates. What are the optimal doses? Crop dependent, context dependent. Use sap analysis to verify. Question from Clinton, do small grain crops have an equivalent to the black layer stage? I'm sure they have a similar progression of maturity, Clinton. I don't know the answer exactly, but I'm sure they have a trigger point that determines when there is no longer any transfer of sugars that will occur into the kernels. Question from Mr. Anonymous, or Mrs. Anonymous, I have no way of guessing which. In a hayfield, doesn't ammonium form of nitrogen hasten the grass going to seed? Perhaps a 50-50 application of both forms of nitrogen is a good compromise? So, the answer is you're correct. Ammonium will speed up reproduction, which you want on a reproductive crop, but you may not want on a vegetative crop, such as alfalfa hay or kale or spinach. So the best solution is to not apply a blend of 50-50, because what's going to happen is even the 50% of ammonium that you add is quickly going to convert to nitrate. The best solution is to use urea, or to even better than urea is to use an organic protein or amino acid form. Question from Mike. I want to ask about amino acids and their biostimulant effects when paired with calcium. Do you have experience using amino acids like glutamic acid and glycine to help increase uptake of calcium? Yes, I have some limited experience, and yes, they can be very effective when they're the right form of amino acids. Even just standard glycine and glutamic acid, you'll get variable performance depending on the source and depending on the L versus R rotation. Can I theoretically use a soy protein hydrolysate that has high levels of glycine? So you could try it, you could experiment, but yeah, just the point that I made previously is that not all forms of amino acid or not all forms of glycine are going to perform identically. Question from Sally. I have high nitrates, 10 part per million in my irrigation water. What can I do? Well, first of all, 10 part per million isn't high. Secondly, enjoy. You've got free nitrogen fertilizer. Just buffer it out accordingly. When I say buffer it out accordingly, make sure your soil microbiome has enough sugars and magnesium and sulfur and molybdenum, and enjoy watching that convert to bacterial proteins. Question from Ned. Is there an upper limit of foliar nitrogen that should be applied? The upper limit is only determined by the presence or absence of other elements. So as long as the crop has high enough levels of magnesium and sulfur and molybdenum and other nutrition to support healthy vegetative growth as you build more biomass quickly, you can add a lot of nitrogen through foliar applications and through repeat applications. Question from Clay. So if excessive nitrates create a yield drag, what can a farmer do to reduce those effects? Yeah, I didn't include enough information in the slide deck, and I answered this question partially earlier when I gave an example program, but the conclusion is actually pretty simple. It's the bottom line summary. Don't apply nitrogen in any form until the crop needs it, or a week or two before it needs it, and then apply it in the form of urea. That's how you remove yield drag, and that's how you get the greatest yield responses. Question from Ken. When you refer to yield drag and net energy per yield, I assume you're always referring to fruit seed yield in a forage context, when the goal is to maximize total digestible nutrients per acre, but also to provide amino acid nitrogen to our rumen myome rather than NPN, non-protein nitrogen. How do we balance nitrogen forms to achieve this balance? Ken, my recommendation again would be to use urea and to combine that with the other elements that I spoke of, the sulfur, magnesium, molybdenum component. That's going to give you vegetative growth. And the net energy for yield component would still hold true in a vegetative crop. Question from Brian. Is management of excess of soil nitrate with a Hania test different than management of excess sap plant leaf nitrate? I mean this in terms of long-term soil health, like high carbon and nitrogen nutrient cycling covers, humic acids, bacteria, fungi, versus short-game plant health and foliars with balancing nutrients via sap analysis. Is management of excess soil nitrate different than management of excess of sap nitrate? If I'm understanding you correctly, I think the answer is no. Well, there are different tools being used. So with excess of sap nitrate, we can put on foliar applications to quickly convert that nitrate to complete proteins. Whereas with excessive soil nitrate, we are using different tools. You're using carbon, using cover crops, but you're also still using sulfur, magnesium, and molybdenum. So similar nutrients, I guess, would be used in both soil and plants. I hope that's the right answer, and I hope I understood your question correctly. Question from Holly. In our area, it's common to use urea and ammonium nitrogen sources. Could you quickly discuss some of the factors that influence the rate of nitrification to illustrate why those sources might not be inherently safe? I seem to have a problem discussing anything quickly, much less the nitrification process. But the short answer is the speed of nitrification is, as I understand it, majorly determined by three things: the soil's oxidation state, soil temperature, and soil moisture. So temperature and moisture are fairly straightforward, and they appear obvious to me. Basically, you can think of your soil as a bacterial petri dish, and the more ideal temperatures you have and moisture levels you have for bacterial populations to thrive, the faster the nitrification process is going to be. The third factor is going to be the soil's oxidation state. So when you have oxidized soils, and I talk about this in a number of other webinars as well that you can link to, when you have oxidized soils, those can be bare soils that are exposed to sunlight, soils that have had lots of tillage and the introduction of a lot of oxygen, soils that have had limestone applied, or soils that have had lots of salt fertilizers applied. Basically anything that has an oxidizing effect or a weathering effect. That will also dramatically speed up the nitrification process. So sadly, many of the things that we do in mainstream agriculture tend to have an oxidizing effect, and they will speed up nitrification. Question from Hunt. Do you think including calcium in a post-tassel foliar application in corn would aid in preventing premature placental cell death, thus increasing the grain fill period? Maybe. If it were chelated calcium, I don't know. My preference would be to make sure that all that calcium gets into, or large amounts of calcium get into those developing grain embryos during the cell division period immediately after pollination. So my emphasis would be on getting large amounts of calcium to be absorbed from the root system upwards during the tasseling and pollination period. And I think that's likely where you're going to produce your greatest response. Question from Ken, how much nitrogen needs to be applied early for corn? I already gave an example. We very seldom apply nitrogen before V5. And usually, when I say usually, let me quantify that. I'd say greater than 80% of the time, our sap analysis results coming back at V5 show that the crop has excess of nitrogen at that stage. there's not very many ounces per acre of nitrogen required by a corn plant 6 inches tall. There's just not, and there's plenty in most soils to supply that. The peak nitrogen demand usually happens later during the grain fill period. Question from William, is 200 pounds broadcast of AMS at corn planting generally a good idea? Not in my opinion. I would prefer to save it until later. Question from Miss Anonymous, can nitrogen efficiency program be applied to granular urea? Yes, with some adaptations and some modifications it can. Might need to switch to using some dry ingredients instead of liquid ingredients, because you can only apply liquid up to a couple liters per ton before you start clumping. Depends on your application type as well, but the short answer is yes, it can be adapted. Can excess nitrogen result from the application of finished and well-matured compost? From Tom Willie. I have not seen that yet, I don't think. If you have a broad carbon to nitrogen ratio in mature compost, like a 20-to-1 or 30-to-1, I haven't seen excess of nitrogen result from those types of applications. Have you ever tried a liquid AMS 8009 instead of ATS for liquid sulfur source? My understanding is that the sulfur would be more readily available in this form. From Danny. Hi, Danny. I have not, don't think I have experience with that. I think a few of our growers are doing that, but I haven't personally observed it. So I don't know. I know that we're generally quite satisfied with the response we're getting from ATS. But it would be interesting to dig deeper into that and try to understand better what's going on. Question from Hunt. Hunt, you asked the $1 million question. How do you feel about nitrification inhibitors to slow the conversion of ammonium to nitrate? Do these negatively impact overall soil biology? You asked the right question. My understanding is that yes, they do. They do negatively impact overall soil biology because they impact a lot more than just the nitrification bacteria. So, and the same goes for the urease inhibitors as well. So, putting on urease inhibitors also really does a number on soil biology. And I haven't done my homework. In fact, I don't know that anyone has really looked yet at how nitrification inhibitors and urease inhibitors will affect the rhizophagy cycle, but I can't imagine that they don't affect it negatively. I would be really surprised if that were the case. Question from Stan, how long shall we wait to apply organic nitrogen and ammoniacal nitrogen on blueberry crops after we apply ericoid mycorrhizal fungi together with humic acids and organic matter? That's a good question. I don't think you'd need to wait for an extended period. At most 10 to 14 days. If you're successful at getting your ericoid mycorrhizae in close proximity to the root system, I would expect colonization to happen pretty quickly. And at that point, neither of those nitrogen sources should have a negative effect on colonization anymore, as I understand it. When using dry urea, could you impregnate humics or blend dry humics with the urea? The answer is yes. Something that we recommend pretty frequently. Using humicarb at 2 liters per ton is a common recommendation for us. Actually, I shouldn't say it's a common recommendation because we prefer using liquids, but we have experimented with that. So, a question from Danny. There seems to be a fair bit of research showing optimal yield increases coming from a 1-to-1 ratio of applied nitrate and ammonium. Why do you think that is? So, Danny, here's the deal. All of nitrogen fertilization and all of agronomic advice, or the vast majority of it, is all framed around mineral nitrogen. Nitrate versus ammonium, and sometimes versus urea. The historical literature and the historical research does not include the rhizophagy cycle. It's completely absent from the conversation. And what I'm advocating is to shift our nitrogen management to use the rhizophagy cycle first and foremost, and then supplement with ammonium or nitrate as needed. So, and what all of our field experience shows, and that's a lot of field experience, millions of acres at this point, optimal yield increases are going to come from rhizophagy cycle nitrogen, not from a 1-to-1 ratio of nitrate and ammonium. Now, if you're growing in a hydroponic situation, or if you're relying only on mineral nitrogen, then the 1-to-1 ratio might be appropriate or relevant. But if you're using bacterial proteins, bacterial or microbial nitrogen, that whole math goes out the window. So thanks for asking that question and for giving me the space to try to clarify that. Question from Andrew. I was using nitrogen efficiency program last year after switching away from ammonium anhydrous ammonia. I was using UAN side dress on corn in southwest Iowa. My problem is I can't side dress all my fields because of the slopes and curves and odds and ends. I had a company spread dry urea over the top on some acres. I feel both methods didn't work well. The weather was too dry, and the dry urea didn't get worked into the ground. I had them treat with humic acid and add some sulfur to it. The plan for 23 was to side dress UAN before planting so I don't damage plants, and I was going to double the rates of humic and sulfur and add more carbohydrates to try to stabilize it longer. Everyone has excellent luck with anhydrous ammonia due to the ability to get it done before planting. It stabilizes by killing all the microbes around it, etc., and so far has been a painful transition. I hear you, Andrew. That sounds like your transition has been a lot more painful than many of the growers that we work with. So I think this would merit a conversation, a follow-up conversation offline where we can dig into the details a bit more deeply. But yeah, obviously you have weather challenges and logistical challenges, both that need to be overcome. So I like your plan for 23. I think that is a considered next step, a reasonable next step, and it'd be interesting to see what further next steps can be taken to help through the transition so that you don't have any further pain through that transition. Thanks for your comments. Question from Matt. Do you believe that sap nutrient results ranges are correct for winter wheat? I don't have any particular reason to not believe that's the case, Matt. If you have reasons to believe that they are not, then I'd welcome hearing from you. Question from Craig on corn. When do you run a sap test if you want to foliar correct an issue? There's several correct answers, but the one correct answer is 2 weeks before you intend to do the foliar application. Question from Darren. Currently set up to apply only granular products at seeding. What would be recommended product placement at seeding? This is small grains in Western Canada. Darren, I'd want to dig deeper into understanding soils and everything else that's going on, but I would probably pick either ammonium sulfate or urea or some combination of both. And I'd like to add some humic substances and other materials to that as well. Question from Stephen. Is it feasible to grow your own microorganisms using your own farmland leaf mold habitat and inoculate those with molasses in a biochar medium and incorporate that into the rhizosphere? Yes, Stephen, it's feasible to do that, but that's not a replacement for adding nitrogen fixing bacteria and specific inoculants. And this is my point of view comes from a very practical perspective, just a practical place from lots of experience we've had with people who have developed their own microorganisms. And you can certainly do that, but it's a false assumption to assume that everything your soils would benefit from is in the native habitat around you. That's going to vary a bit dependent on plant species. Just a simple example would be rhizobium bacteria. If you're growing legumes, soybeans or alfalfa or clover or something like that, they're likely to benefit from rhizobium inoculation or from soils that have had a history of rhizobium and legumes in a rotation. And so if you propagate species from a native habitat, unless you include growing legumes as a part of your propagation, you're unlikely to propagate rhizobium. You're also unlikely to propagate mycorrhizal fungi. So while those types of tools can be useful, they're not enough in and of themselves in my experience. Follow-up question from Greg. When is the best timing to run SAP tests? Craig, I would suggest reaching out to the AEA team and having that conversation with them, because they've put together a protocol of what the best crop stages are to then follow up. Usually our approach is to do pre-side dress, pre-tasseling, and I think there's maybe one other spot in there as well, where we're pulling SAP samples so that we can follow up on if there's a need to make any corrections. And again, this is dependent on application capabilities and management capabilities. Question from Niels. How do we determine carbon mixture rates for liquid manure? Is it by percentage of ammonium in the manure? Niels, it's a bit more complicated than that. You also have to look at the bonding capacity or the chelation capacity of different types of carbon is going to vary significantly, and it's also going to vary based on particle sizing. So our humicarb, for example, will effectively bind all the ammonium in very concentrated liquid manure at rates of 1 gallon per 5,000, some cases as little as 1 gallon per 10,000. But you're talking about a material that has a couple micron sized particles and still is very robust. So most materials, it's going to take quite a bit more than that. Don't have a good answer for you, unfortunately. Question from Tanasha. What if we apply poultry manure with molasses? Will it resolve the conversion of nitrogen to nitrate as we try to increase the carbon content in the poultry manure? So that will help, but I would actually suggest adding humic substances to the poultry manure instead of molasses. That's going to give you a rapid carbon spike and bump. What is the another follow-up question here from Niels. What's the optimum timing for soil applied nitrogen to wheat? 40 units is permitted. Additional foliars are also permitted up to 40 units. What's the best form of N to apply to the soil? My preference is ammonium sulfate and urea, dependent on what's going on in a specific soil. And that's your last question. Your first question, what's the optimal timing? That also depends on what's going on with that soil and stage of crop, but I would say it is going to be after breaking spring dormancy, generally, usually a couple weeks after dormancy break. Question from Miss Anonymous. If you don't have access to humicarb, would higher concentrations of humic acid products extracted using potassium hydroxide be required in the nitrogen efficiency program? Yes. We've found that the very best humic acid products, it takes at least 5% to match 3% of humicarb, and most it requires upwards of 8%. So there's definitely a jump up. Question from Eric. While we're trying to transition to biologically based inputs, we are still seeing better yields with 28% liquid nitrogen in wheat than we are with non-synthetic forms of inputs. What is the ecosystem holdback that is keeping us from being able to show the results that we believe but just haven't seen yet? Eric, I'd need to know a lot more for me to be able to answer your question. But if the short answer is if you're still seeing better yields with liquid in, then that means your soil biology hasn't yet recovered to the ability to be able to supply the majority of the crop's nitrogen requirements. So I'd start asking lots of questions about timing and quantities. What's the timing of your applications? Are those applications being buffered out? And what are the amounts being applied relative to the crop's needs? So those are the types of questions that I'd start asking to try to figure that out. And if you want to reach out to the AEA team, I'd be happy to have a follow-up conversation and dig deeper into that with you. Question from Bo. Hi Bo. Can you explain the difference between urea and methylene urea? Yes, I think I can. I've used a product with urea, methylene urea, and triazone for foliar applications. You're not going to be happy with the explanation, Bo. Triazone urea is produced using a reaction with formaldehyde and something else. I forget what it is right now. I dug deeply. David Miller also gets a lot of the credit. The two of us dug into this quite a bit a couple of years ago when we were working with strawberry growers in Florida, and we made a recommendation for urea applications. They were fertigating on plastic with drip irrigation. They started fertigating with triazone urea, and we got a significant drop in microbial activity and in overall plant health and energy. It was just like we had a negative effect, noticeable negative effect to the triazone urea. And yet we're having positive effects where quote unquote conventional urea is being applied. And so we dug into what is triazone urea and how is it different and why is it different. And it's a different manufacturing process. It's manufactured by reacting formaldehyde with one or a couple of other ingredients. I forget now. And supposedly the formaldehyde completely disappears and is converted during the manufacturing process. Well, I have no basis for disagreeing with that. I don't know. But what I do know, without any doubt, is that triazone urea did a number on soil biology. It really suppressed soil biology in some very significant ways. So my advice would be run. Question from Matt. How do you know when a wheat crop needs nitrogen? Yes, we do use sap analysis, and even right after dormancy break, when you have leaves that are just 5 to 6 inches tall or long, we'll start pulling samples. That'll be when our first sample is pulled. Daniel, I've never heard of 21% urea being available. Can it be made by mixing dry urea into water? So yes, when you mix dry urea into water, into hot water at its maximum concentration, you can create a 21% liquid urea. It's not commonly advertised as being available. We have a number of growers that we've worked with whose suppliers have been mixing it up for them. And it's going back to the conversation about a pound of nitrogen not being a pound of nitrogen. Getting urea liquefied for you will definitely be more expensive per unit of nitrogen. But based on the amount of money spent for nitrogen versus the crop response, it usually produces the greatest ROI and the greatest economic crop response. Let me see. Question from Austin. When is the right time to apply turkey manure in corn? Austin, it depends on your soil carbon content and the application rates of turkey manure. I would suggest a spring application, but there's a lot of context there that's going to be important. Please reach out to our team, and happy to dig into that in a bit more detail. A question from Nick. Is applied nitrogen to a cover crop an agronomically and economically efficient way to feed the subsequent crop? Nick, the answer is it can be sometimes. It depends. It depends on the type of cover crop. Is it a legume? Is it a grass? It depends on the stage of maturity at which you incorporate that cover crop or at which stage you kill it. If it's young and relatively immature, the nitrogen is going to release pretty quickly and it's quite effective. If it's very mature, it's going to be a lot less effective. So again, lots of variation there. Can't give you a good answer other than to say that yes, it can be if it's managed to deliver that outcome. Frederick asks for my thoughts on nitrogen in rainwater. It's my main source of water on the homestead. My understanding is it's usually, I don't think you usually have much nitrogen in rainwater as I understand it. It can be in well water mostly. Question from Matt. Our chalky soils have high pH. How can we get calcium into our crops? So this is deviating from the topic a little bit, but I'll bring it back to nitrogen. A, you can make sure that your plants only absorb ammonium and not nitrate. B, address boron and make sure that you have generous levels of boron. And C, you might need to use sulfur to try to bring the pH levels down a little bit. Question from John. We apply the AEA nitrogen program in the fall, and John is growing stone fruit in California. We often also apply a soil primer program. How much time should we give between the two applications? Well, John, the two would have a synergistic effect and not an antagonistic effect. So I would say generally you can tie them as close as 5 days to a week apart, up to a couple weeks apart. But I would expect you would see synergistic effects and not antagonistic effects. Question from Marion. How do you like in-furrow liquid fertilizer or 2x2 liquid or dry? Some record growers claim corn root should find the food source before the seedling gets out of the ground. So the short answer is I like in-furrow applications or 2x2 applications of plant nutrition. I just don't think that those applications should contain high levels of soluble nitrogen because that's going to limit or slow the rhizophagy process. So I think in terms of positioning and timing, those are great applications, but I wouldn't want them to be high dose nitrogen applications. Question from Craig. Is the Haney test used for determining if a plant is taking up biological nitrogen? No. The answer to that would be, well, I guess to some degree, the Haney test will be used to determine what forms of nitrogen are in the soil profile. And then you can use a sap analysis to determine whether the plant is actually taking up enough nitrogen. Is there a benefit to adding humicarb and or the full nitrogen efficiency products to poultry meal? Typical analysis is 10-0-0. Humicarb, maybe. Bryce, it depends on timing, crops, depends on the amount of carbon that's in your soil. Again, there's just lots of variation here. For organic growers, how would you adapt your product recommendations? In general, the big question is, does your soil have enough sulfur and does it have enough carbon to assimilate all of the quote unquote organic nitrogen that you're adding without having it converted to nitrate? If the answer is yes, then you're likely to get a limited economic response to the nitrogen efficiency program. But if the answer is no, then it'll be very worthwhile. So I would suggest perhaps adding gypsum in with your 10-0-0 as a source of sulfur, or another form of sulfur if that's more relevant for your soil context. And I would suggest adding humic substances like humicarb. So if you have sandier soils or if you have soils with low carbon availability, then I would definitely add an adapted version of the nitrogen program to an organic situation, to an organic application. That's a great question, Bryce. Thank you. John Warmerdam came back with follow up on my comments on triazone. Triazone urea is a reaction of urea, formaldehyde, and ammonium. I'd expect that what it might convert to in the plant applied as a foliar might work out, but in the soil it's going to break down to its components. Thank you, John, for that research and checking that out and bringing that to the conversation. Is there a worse product to put in your soil than formaldehyde? Yeah, probably. I would say anhydrous ammonia and fumigants are probably match it in terms of negative crop response or soil response for the long term. So that's my opinion anyway. So I want to say thank you to all of you for being here and for sticking around. Wow, it's an hour over time. I hope that you found this useful and informative. And we're going to do another webinar on a related topic to this in the next couple of weeks. It hasn't been announced yet, but please sign up to our newsletter. And if you've found this useful, then I would really invite you to share it with your neighbors and friends and get more people to show up for the next one, because that's how we all make a difference in the world, is sharing what we've learned and what we know with others. So thank you all for being here. Have an awesome growing season. We'll talk to all of you again soon.